Hello, and welcome back, and hopefully you've answered this question from the previous part of the video. So, hopefully you realize that as the kettle boils, the amount of water in it is decreasing, so that's clearly not conserved. But that water that is leaving the kettle ends up as water vapor in the room, and so it's the total amount of water in the kettle in the room that's conserved. This illustrates something that's generally true about conserved quantities. It's not that the, say, momentum or energy of individual objects or of systems is always conserved. It's that when those quantities change, it's because they've been transferred from one thing to another. So, for example, when you have a mass oscillating up and down on a spring and you reach out and grab it, its energy decreases, but that seemingly lost energy hasn't disappeared, it's just been transferred from the mass to you. Another theme in this course is the interplay between measurement and calculation, experiment and theory. So let's think in general about why we make measurements. We make measurements for lots of different reasons, but it mostly boils down to that measurements help us make decisions. Decisions like how much flour is enough for my bread, or how long should I cut this 2x4, or maybe more complicated and controversial decisions like what would a good tax level be to pay for healthcare. During labs in this course, you might make measurements to determine whether you can ignore friction acting on carts as they collide. A chemist might make measurements to determine whether the chemical reaction they just carried out has produced the chemical they think it has. They might get spectra, which is just a lot of measurements. And an engineer might make very similar measurements to determine whether the scrubbers are working for a coal plant. For scientists, overall, the reason to make measurements is to test hypotheses. We will use a theory to make some prediction about what a quantity ought to be according to the theory, and then we will make measurements in an experiment to see whether the measurements agree with the theory. On the flip side, why do we calculate rather than measure? In general, we calculate to help us make predictions, which sometimes lead to decisions. For example, a prediction which takes a lot of calculation is what will the weather be like tomorrow, which could help you decide whether you should go on a picnic, or whether you should irrigate your fields, or if you're living in New Orleans in 2005, should you evacuate? But again, the reason scientists usually calculate is to test hypotheses. We predict by calculation what the result of an experiment will be, then we do the experiment and see if our prediction was correct. I hope you've been taught about the scientific method, so I'm not going to spend a lot of time on it, but I will point out that in these video lectures I'm going to tend to work from observations to hypotheses, and so I thought I would spend a bit of time pointing out how it works. We usually start with observations and we look for patterns in them. From the patterns, we make a model. This is an example of inductive reasoning, moving from specifics to general rules. A model is an example of a hypothesis, which is just an explanation or a proposed explanation of some set of observations. That allows us to calculate and make predictions. We now test our predictions in experiments by making measurements, and we compare the measurements to the calculations to see how well they agree. If they agree well, then that gives us more confidence in the model. If they don't, we will have to modify our model or even discard it. This shows that our knowledge is provisional. It's always subject to being tested. If the model passes many tests, we may begin to call it a theory. A theory is a model that has been well tested and has passed the tests. Eventually, if we have a lot of confidence in it and it makes a lot of different predictions, we may call it a law. Note that this is a model of the scientific process, and like most models, it's a simplification. The real-world process of science is usually quite a bit messier and more complicated than this. Not all hypotheses are equally scientific. And so you might ask what's required for a hypothesis to be scientific. The main requirement is that it has to be testable by observation or experiment. And in particular, it's certainly not a scientific hypothesis if it's impossible to disprove. In one word, we say that a hypothesis must be falsifiable, which just means possible to disprove. When we make a model of a situation, if we include every detail of the situation in the model, we usually end up with a model that's so complicated that we can't use it, and so simplifications are usually necessary. Let's take an example. That funny-looking creature there is me, and let's say we want to model the process of me walking across the room. What color I am probably makes absolutely no difference, and so there's a simplification. But as well, my exact shape probably doesn't matter. It's probably sufficient to know where my head is, know where my torso is, and so on. But maybe we don't even care about how my head and my torso move individually and only care about how I move as a whole, but perhaps we need to know whether I can fit through a door. In that case, this might be a good enough model. And maybe we don't even care about that, and we just want to track my position. And so we could choose a representative part of me and represent all of me by the location of that representative part, a point. This is something we call the particle model, and we'll use it all through this course. What we see here is a progressive simplification from a concrete representation of me to a more abstract representation. When something is moving and we don't care about its shape and it isn't rotating and it doesn't have internal motions going on, we'll often represent it just by a point using the particle model. And then we can represent the motion by showing it at various different times, often with velocity vectors in between. This is called a motion diagram, and I'll talk about it more later in the course. A more abstract but also more powerful representation of the motion would be a graph, such as this position versus time graph. And an even more powerful and more abstract representation would be an equation.